Welcome back. Now we get to touch on one of those famous words we hear in quantum mechanics, Hermitian and Hermicity. In this question, we wish to show that if H in the inner product bracket with Q hat on H is equal to Q hat H inner product with H for all functions H that live in Hilbert space. Then we have FQ on the right hand side with G is equal to Q on the left hand side with F with the inner product of G for all F and G in the Hilbert space as well. Okay, what this is really showing is the definition of Hermitian in just two different ways. Meaning, going back to what we had in the book, if we see that the operator is on the right hand side, it's equal to the left hand side given that we have any f of x in the Hilbert space, blue H. But we were also shown that we had f of q with it acting on G is equal to, similarly, it acting on f for any f of x and g of x in H. These are just definitions. We have to see why, but it helps to think about these in the inner product. And now we'll move on to what it actually showcases. So let's break this statement down. In the solution, if we're given this condition of Hermicity, let's go ahead and break the left-hand side down into 1, the left-hand side down into 2, and apply a substitution of letting h of x equal f of x plus cg of x. Okay, where c is some constant, and that could be complex, could be real, but what we want to showcase is that it is a constant. And if you have a little hindsight, you know that this is setting up for a case of linearity. All right, so then if this is true, our goal is to prove that if H, F, and G are in the Hilbert space, then we can showcase how to do this. So let's plug in here into 1, and we see here that we have F with plus CG, and then Q on the right-hand side acting on F plus CG as well. Okay. What this is a process or a property that's called linearity, where I could take Q and distribute it into something here and just have my factors. This is a property from linear algebra. We like it, we love it, we need to use more of it. But because of the way the Hilbert space is formed, we know that this is a vector space and this is a property of the vector space. And it's a very useful property. We've seen it in integrals and differential equations. That if q was a derivative, you know that you can apply the derivative to the function f and the function g, no problem with the constants coming outside. So we call derivatives a linear operator. But, there's a whole host of operators, so we can generalize it to q. Nonetheless, let's see how we apply this to the given context. Here we see that we have a blue plus sign here. So if we focus on the left-hand side, we split this up, just like we split this up here. So F plus, and then the second bracket, so we just kind of split that factor out. And now you see here, we could split up the purple factors by distributing in the Q. So we have Q onto F here with the purple plus, and then Q acting on the CG here. Cool. Similarly here, we have CG, and we need to distribute it into this. So we distribute like we did on the left-hand side of the inner product. And now you see, all we have to do is factor out a specific amount of constants, right? But in order to factor out the constants, what we have to realize is that this does represent the inner product, which let's throw back to its definition here. If I have F with the inner product of G, that means in the integral I have F star G. So if I have a constant on the left-hand side, which are my red constants, I have to take them out with a complex conjugate on them. If it's on the right side, like my green constants, then I don't. That comes back down to the definition of inner product as we see here. So that's why we have a C, C star, C star C, which of course we know that this goes to magnitude squared, and our equation gets simplified. So that's how we walk through, the linearity aspect of these, and you'll see this, whether it's written out in this form or not. you'll see this argument being applied in several cases, especially dealing in vector spaces. So best that we be aware of it now. But let's try the left or the right hand side where the operator is on the left hand side of the inner product. Let's see what happens there. Alright, so clearly we're repeating the same linearity process, except now Q is on the left hand side of the inner product. If we recall, going back to what it meant to be Hermitian is that these operators needed to yield real results, so the complex conjugate is equal to the thing itself. And so that was another property that we had, was that Q star was equal to Q, and we could move forward with that. So moving it to the left-hand side was a part of being Hermitian. So here, apply the linearity and work its way through. You could see the steps if you want. What I want to highlight, though, is a little more important in the fact that we need to remember what the given condition was, which was the condition of Hermicity. Okay, so let's recall that again. Here, we see that we're Hermitian if the operator can go from the right side to the left side, right side to the left side, highlight it here in red and yellow for any function that's in the Hilbert space. So we see here that if it holds for the function, h, which was the given condition, then we know that it also holds when we have the forms with the f and g substitutions, because f and g are also in the Hilbert space. What this allows us to do is going to simplify this equality pretty quickly. Pay attention to the color scheme here because we'll see some fancy canceling. So then, okay, we see that if we equate 1 and 2, the left-hand side of the original statement and the right-hand side after the substitutions of a linear product, or a linear combination rather, not product, combination, we see that we have the conditions here of Hermitian on the opposite side of equal sign. So if I minus this over, I have the same thing here, so they cancel. And of course, I have C magnitude C squared, and again I get the Hermitian definition on the G function, so they cancel. So I'm left with a nice consolidated statement just involving the constants. One with C star, both sides, operator on the right-hand side, on the left-hand side of the equal sign, and the operator on the left-hand side of the right-hand side of the equal sign. A little kind of yin-yang there, but we see that now we just need to pick convenient values of C and see what we yield. Of course, it's math and we're multiplying, so why not go with the convenient value of C equals 1? Okay, clearly the complex conjugate of 1 is 1, no big deal there. We can just have this equation. We'll call it equation 3. As you might expect, we have to set up another equation to solve this, so let's C equals I, and see what happens with that. So now that we plug in I, let's note here that this was a plus sign in the middle, but because we had the C star, the complex conjugate, I goes to a minus. Similarly here, I goes to a minus. So then we factor out an I. Again, this is just extra algebra. You could cancel them all right here, be totally fine. Point is, you factor them out, you cancel both sides, and now you're left with two equations, and we can add these two equations together. So adding number 3, where we just plugged in 1, and then adding 4, where we plugged in I, we see that the plus sign here makes the fact that these complex conjugate terms are, that with them being negative, will cancel down. So let's add them up. We see we get 2 factors of this, those cancel. 2 factors of this, those cancel, as stated here. So clearly, the 2's on their factors cancel, and we conclude exactly what we wanted to, which was the second part, or the second definition of Hermitian, being that it could work for any functions. So that's why some authors just don't use this definition, because via linearity, which we already assumed in the vector space, we assumed this was the case. But nonetheless, it's great to work through. I think it's worth getting, your feet under you with some of these definitions, especially if you haven't had linear algebra. I know for me, having to see these out in full detail helped me just calm my nerves. I can only imagine that some of you have nerves as well. Let me know what you think. I think these are fun. although it's a little more math heavy, so now we have to get back to physics. But what this will allow us to do is, especially when we get into like angular momentum and other operators that are a little more complex, it'll save us a lot of heartache later, and certainly a lot of headache. So thank you all for watching. Until next time, stay curious and happy learning.